we're here to work on the take-home test. I put the wrap for most of you are virtual, so I put the wrap-up video. That's up there. Well, what I was telling them was that I also taped third hour outside doing the drill, and so it's about a 6-minute tape, and it's not loading. So I'm thinking maybe it's just too big. I'm trying to reduce the file so that'll load. A link at least will load onto the Canvas, and I'll put it on my YouTube channel. Okay. Anyway, so that's coming. I'll try and get it up before I go to bed tonight. And yeah, anyway, so let me share the screen unless you guys have something you want to talk about.
Mr. Askey, are you recording this?
Yes, I am.
All right, cool. Thank you.
Yeah, so if you can only watch part of it, or, I mean, you know, I need somebody here so you guys can ask me questions. But if you have a particular question, you probably want to stick around. We'll end up going over it. We went through about half of these last week on Wednesday, and that recording is on the Facebook group, and I think there's a link on the Canvas as well. I don't always get to Canvas. I mean, I'm at 50. I was telling them I'm at 50% capacity already on Canvas, so I've got to stop. I can put links, but I can't. I mean, I want room for screenshots. I may have to stop doing that and just put it all on Facebook. Anyway, we'll see. So let me share the screen. We had our first day today, and it was good. All right, went outside. We'll probably be doing some stuff, maybe outside tomorrow. Probably this hallway if we get that far. Okay. All right, so we have 15 people here. That's pretty good. All right, so which questions? Now this is the same document I was working on, and what I'm going to do Sunday. Now this is due Thursday night. You guys can hear me okay? Yeah, okay. So this is due Thursday night by midnight, but Sunday, so you just go ahead and submit it on Canvas. But Sunday, I will put up, like, I'll clean these up, and I'll put up like this one. It's not quite done, number one, and we talked about this on Facebook. There's only a couple of steps left, but I'll complete it. I think you guys are getting something like, anyway, the answer you guys are coming up with sounded about right. But I'll complete these, and I'll clean them up a little bit, and I'll put those on the Sunday night so you can check to make sure you're right, make sure you're studying the right stuff for Tuesday's test. And then for virtual kids, I told everybody today, but it's on the calendar, but there's going to be another Zoom. Our next Zoom will be, other than the wrap-up videos, our next live Zoom would be Monday night next week, the night before the packet's due. Oh, and I'm putting together a cover sheet for the packet. So it just tells you, like, it was already stapled together, so that's already done, but it tells you what else needs to be stapled on there. It tells you what everything's worth, and then you check stuff off, and then I put your scores on there. So I'll have that. By the way, virtual students, I have packet 2 copied off, and it's like 10 pages long, and it's the PDFs are on the Canvas, but if you don't want to print all that stuff off, I have about 10 of them in the box on my front porch. Okay, I apologize. My neighbor was collecting her mail, and she thought that she was supposed to, so she took the box over the weekend. So if you came over to look for the box, it wasn't there. Anyway, it's back on my porch. And I put in packet 2, but if you're in class, don't come get it, because that's for the virtual kids. If I run out of those, I'll make some more. Okay. So questions on the take-home test. That's primarily why we're here tonight.
Can we
Can
do
we
number
do
6?
3? Oh,
Number 6, we'll do 6 and then we'll do, all right, we did not do 6 last time, so let's look at number 6. If it's one we did last time, I'll probably just I'll mention it and then refer you to the other video. All right, so this is a circular motion problem. And so when you're thinking circuit, it does require a drawing. So let's do a little drawing and we can organize a thing there. All right, so we got a hamster running clockwise on a wheel. That is a terrible circle. Golly, that's awful. So the hamster's running clockwise. So the hamster's on the inside of the wheel, but he's running this way. Okay, so there's a little hamster running along. At speed of 75 centimeters per second. So that is a velocity. Well, it's speed, but 75 centimeters per second. Okay, we'll leave it. Okay, so remember I said there's MKS, meters, kilograms, seconds. There's also CGS, centimeters, grams, seconds. So you either need to be in MKS or there's one other that we use, and that's FSS. And FSS stands for feet, slugs, seconds. Those are the English units, imperial units. But normally this is kind of the order we're in things. We're in MKS. The first is the most we do, and this is probably the second most, and this is the third most. So occasionally we do CGS. So maybe we'll just try centimeters, grams, seconds here. All right, so 70, because I don't like decimals. 70 centimeters per second, 75 centimeters per second. What's the omega? So omega question mark in inverse seconds. All right. If it has a radius of 12 centimeters. So R equals 12 centimeters. So it looks like I can get away with just using CGS. All right. Well, we just use our bridge equation, right? I'm not sure when I sit here and work it for you, but I'll work it with you. How about that? So you guys employ the bridge equation. And what you should do, and I talked to the in-class kids about this today, but you have now a reference sheet, your first reference sheet. You're going to have eventually like 24 of them, but you should use that. You should either print off that reference sheet. It's in unit 3 of the Facebook group. And if I haven't already, I'll start a reference sheet in the modules, probably in the reference. Yes, I think it's in the reference module, the module 2. There's a thing that says references. So you'll have eventually all 24 sheets there, PDFs. And then you can always go to the Facebook group. Anyway, so if you have your reference sheet, it has, and you'll get by the way, you get a reference sheet on the tests, on the in-class tests. And I was talking on the wrap-up video, I talked to virtual kids about how we're going to do the test next week. Just looking at my crowd here, many of you are virtual. I mean, some aren't. I applaud everybody for coming. But for virtual kids, I'm going to open up my classroom in the afternoon on Tuesday of next week, Tuesday the 20th, and there's nobody in there. And so I'll open it up. I can easily hold, with good separation, I can easily hold 12 people. Now, you may not want to step foot at Norman High, and in that case, you wouldn't go for that option. For you, it would be to, you would do it partly through Zoom or something. Or maybe outside on the West Lawn, but then you don't have Wi-Fi. Well, you don't need Wi-Fi. I don't know. I'm thinking about it. Back to this now. So you have your sheet. And so we say V's equal to omega R. That's the bridge equation between linear and circular world. We're trying to find omega. So omega is simply V over R. And the units work out nicely, and we'll end up in inverse seconds. And so I'll let you take it from there. That's the idea. Now, the ones on the test, and maybe you may have heard me say this before, but the in-class test as a whole is always easier than the take-home test. So I want you to, I don't want to give you a big surprise. I want to reward you for what you're doing right now, for showing up to all 23 of you, for showing up on a Monday night on your own time and working on this take home test. So your big reward is going to be next Tuesday, not tomorrow, but the week from tomorrow. When you take the test, you go, oh, I remember this problem. It'll be the same kind. It won't be a hamster and a wheel. It'll be a mouse, and it won't be going at the same speed, but it'll be the same kind of problem. Maybe not solving for the exact same thing, but it'll look familiar. Okay, next question.
Number 3.
3, we have not looked at that one. And once again, we're doing circular motion again. That's always, circular motion is always hard for kids. It's just, you do it all the time, but let me see if I can make a better circle. Yay. All right, so we'll let the computer do it. So now we have an ant crawling. Can you see that? Yeah, you can see that. An ant is crawling on a 1/3 of the way around a large spherical granite rock. So say the ant starts here, 1/3 of the way around is about right to there, 120 degrees, right? So the ant is crawling, and what's it say, clockwise or counterclockwise? How many minutes will it take? Doesn't matter, it turns out. Oh, no, it's okay. Omega is positive, therefore right-hand rule. I remember right-hand rule. So the ant must be going counterclockwise. So it's a positive omega. Something you may have forgotten. Okay. Remember, I'm not so much into memorization on these things. It's more like, can you apply these? Eventually you're gonna have 24 pages of equations and problems. You're going, well, I don't know where to apply it. That's where the physics comes in. Is how do I apply all this stuff? Anyway, so how many minutes? So we're trying to find t. T equals question mark minutes. Circle that. Will I take an ant to crawl a third of the way? Okay, we got a third. So a third, might as well do radians here. So a third the way around, I haven't even read the problem really that much, but would be 2/3, right? That's 2 pi times 2/3. 2 pi times a third, excuse me. 2 pi is all the way around as far as radians go, and divided by 3. So that's my delta theta. Okay, maybe it's not going to help, but that's important, I guess. Around a large spherical rock has a diameter of 6. I'm not going to fall for that old trick. If it says diameter, remember I want the radius. So the radius is 3. R equals 3 meters, 3.0. If the ant's angular speed, okay, so omega then is 2.02 radians per second. Okay. Now that may be, that may be fast, that may be slow. It all depends on the radius, right? Because we were seeing that the Dagon International Space Station, which moves at 17,500 miles an hour, is like 0.0000. It's real small omega because the Earth's so big. But this is just a spherical rock, okay, which is still pretty good size. It's 6 meters. It's 18 feet in diameter. All right. Yeah. So what looks like once again, we're trying to find minutes. We're trying to find time. So once again, we're going to use this old V is equal to omega R bridge equation. This time we're solving, we're solving for time. And you go, I don't see any time here. So now what would you all suggest we do? We're trying to find time.
Omega equals delta theta over t.
Very good. So we're going to now substitute in. We know that omega equals delta theta over t. And so I'm going to substitute that right here in for omega. We're going to do a derivation later on this week, our first really decent derivation. So we now have V equals delta theta times R over t. Fair enough. And we're trying to find t, so let's solve this for t. This is my first time to work this in a couple of years now. T then is delta, so I'll make mistakes too. Delta theta, I'll do it the dumb way probably. Delta theta times R over V. Yeah, I'll just move the t, switch the t and the v. And so that's my equation. That's going to give you, probably if you did that much, you already got 6 out of 10 points. So bingo, I got everything. I got V. What? No, I don't. Oh, that was dumb. I know omega. I don't know V. What am I thinking? Okay, sorry, it's my bad.
Don't we have omega and the radius so we can solve for velocity?
Yeah, right. So you have omega. Yeah, yeah, okay. Yeah, that's another way of doing it. I'm trying to think of a faster way to do it. You could do omega times R, that gives you V, and then you know that delta S equals V times T. You can say, well, T then is delta S over V. Yeah, I was trying to think of a more clever way of doing that, but you're right. That'll work all right.
What about delta S equals omega RT?
Yeah, so let's go this delta S. Now delta S equals, by definition, delta S over R equals what? Delta S over R equals delta theta. So delta S equals R delta theta. Nah. I mean, that you could do it that way too. Okay, sorry, I'm just confusing everybody. This is kind of what you think through a problem though. I don't like quickie recipe problems. It's good just to kind of, point is there's different ways to solve a problem. There's various ways. So let's stick with one and do it. I'm going to go with the V is equal to omega R since I was given those two. Okay, so V equals omega R, 0.02. Always check your units. Inverse seconds times R, and R, which is 3 meters. So V then is 0.06 meters per second. That's pretty slow. 6 centimeters a second. That's pretty good for an ant. All right, because see why I say, I'm not just saying that to be dumb. I mean, you've always got to think, because this is physics, this is not math. Like if I come up with 0.0006 meters per second, I would have thought that's just too slow. That's even too slow for an ant. So 6 centimeters per second, it's about 3 inches. Okay, that seems reasonable. All right, so
Wouldn't
that's
it be
my
centimeters and not meters?
Do what?
Wouldn't it
Well,
be
it's
centimeters and
0.06.
not meters?
It's 0.06 meters per second, right? Which is 6 centimeters per second, right? 0.06 meters is 6 centimeters. So what
Wouldn't
I'm
there
saying,
be just
0.6 centimeters per second seems about right. Okay. I'm not done yet, but that's a quick check to make sure that everything makes sense. Okay. So that's how fast he's going. And then he's going to go 2/3 the way around. Well, no, not 2/3 the way around, 1/3 the way around. So my circumference then is 2 pi r. So the delta S is going to be 2 pi r over 3, right? Because it's 1/3 the way around. Does that make sense? That's how far he goes. And so, sorry, make this a little bigger. Yeah, so delta S, then we also know that delta S equals V times T. I'm trying to solve for T minutes. So T then equals delta S over V. My delta S, I'm going to stop here. I'll let you do the rest, but my delta S is 2 pi R over 3. My V, I think I did this the dumb way, but that's okay. I shouldn't call it the dumb way, just one way of doing it. My V is 0.06. There's always the perfect, most efficient way to solve a problem, but I am famous for not finding. Eventually I figured it out, but a lot of times I just kind of hack away at it till the daggone thing gets solved. Anyway, so that will do it, except like, what's my problem though? if I plug those numbers in and I plug in 6 for R, oh, yeah, that really is a dumb way. Because if I would have done it, I didn't even need the R in this problem. I bet R's would have canceled. I bet the R, that might be something I do to you on a test where I give you the same problem, but I don't give you the radius. And with symbols, the R would cancel.
Yeah, that's what I did too. I
Yeah.
did E equals delta S over omega R, and then
Yeah,
both.
do it in symbols. Am I talking to IO, right? Do it
Yeah.
in symbols as long as you can before you do what I did. And I know what you're saying. So you did it all and then just canceled your R's, right? Yeah, that's the smarter way to do it. And when
That's what
I
you
do
in
the
silent
key,
help video.
when I show the key, okay, boom, because there's a help video on this one. All right, because I know I did this better in a smarter way. But when I make up the key to this, to my note to myself, on the key, I'm going to cancel R's. I'll show you how to do that. And keep it in symbols. So on the key, I'll do a little nicer. Hey, there's nothing wrong with this method of doing it here. It's just, it was extra work. And, who cares as long as you get the answer. But the problem with this, still, when I plug in numbers, what's going to be the problem for my T?
Wouldn't you need to turn seconds into minutes?
Yeah. So I'll get some kind of seconds, and then I've got to make sure I divide by 60 to get it in terms of minutes. Okay. So solve from there, but be careful on minutes. But in minutes. So just that could be one last move you do at the end. Just divide by 60 and you got seconds in terms of minutes. So I'm going to make a note here since we're taping this. This is the dumb way. I shouldn't say dumb. It's the long way. Okay. That's not nice. It's the long way to do it. Okay. I'm calling myself dumb, but All right. So if you want to know the fast way of doing this, watch the help video on it, or just check my key when I post this thing next Sunday night. But I've nothing against this. This looks like a bunch of crazy chicken scratches, but I accept this as work. I would think this is fantastic in class or on test. All right. So I totally messed that one up. But let's keep going. What do you got?
I've just got a small question about 15C.
Okay. 15C. Let me find it first. 15C. And we started on that one. Oh, what's your final position?
Yeah, like how would you go about finding that?
Well, okay. So you already have that. Actually, it's right here. This is my final position, but you have to give a coordinates on that. So the easiest way to do it is add up your X's, add up this 34 meters plus 39 meters. So that's 40. So what is that? 40, 70, 73. So 73. So you do coordinates. You just give coordinates. So 73 over, and then as far as up, you got 10 meters up. Put a little note there. You got 10 meters up there. And then here you started at negative 15, you went 34. So 19, right? 19 plus 10. So it looks like 29 would be your, so it's a coordinates. You're looking for coordinates. I'm not going to write that down because some people are going to watch the video and they're going to turn the sound off. So I'm just going to verbally tell you that. All right. So you have to listen to know that. See, I'm getting smarter. I'm onto your tricks. Now, last time we did not finish this problem. I had Carlos was asking me about this today in class, at the end of class. And so this was 30, hold it. Now, as far as time goes, it said it was 5 seconds for the second phase, right? So I know this base is 5 seconds, 5 seconds, 5 seconds. But I've got to finish it. I didn't want you to think that we're done, because we never plugged in. Well, for X, this is X. We went 10 meters, right, in the second part of it. So we started at -15. We ended up at 19 plus 10. So we're up here at 29, which is like right there. So this is your green triangle. All right, those aren't vectors, by the way. So this is 10. And then on the Z, you went 39 meters. So you were at 34 on the Z. Uh-oh. Oh no, okay, 34. Almost thought I messed up there. Okay, so went 34 over on this first part right here, went 34 meters over. And then we went 39 meters over. So I got to represent that on the Z versus T axis. So I was at 34 plus 39, I said 73. Yeah. So I'll go all the way to 73 on this one. 40, hold on, I marked too much stuff off. Okay, 40, 80. Okay, so we're to 73, it's 60, at 73 is right here. And then that is going to be the next phase of the green. It helps to make different colors. And then your slope, this slope here will be Vx2, and this will be Vz2. So you got to find 10 over 5, right? That's easy. So that's 2. These are meters per second. Yeah, meters per second, right? Yeah. So 2 meters per second. And the Vz2 is 39 up, 5 over. So whatever 39 divided by 5 is, a little less than 8. Whatever that is. I'll let you do that. Okay? I worked more than that than I wanted to. But I didn't want to leave you thinking that it was flat. Okay. I guess I answered your question on 15C then.
Yeah.
Now, today we did pinwheels, and what? I lost it. The pinwheel problem. Oh no. Okay, let's go back. I got it here. Number 16. That's the pinwheel problem. Let's just look at this problem for a second. It says, from the courtyard activity we did today, assume the class lines up along the breezeway sidewalk facing north, which is exactly what we did. The line of students does a pinwheel, like spokes in a tire. We're keeping straight. We try to keep straight. We do a pinwheel, 90 degrees, pi over 2 radians, and ends up facing east towards the main building. Okay, same thing we did. Suppose your particular radius from the axis of rotation is 32 feet. So here's the science building. So there's the person, and then you're, say you're right here. This is you, and this is 32 feet. That's your axis of rotation. That's your R. It's 32 feet. It takes the line of students, let's say 16 seconds. So T is 16 seconds. And so, boom, so that's what you know. And then it says, determine your omega. What are you going to do there? Remember, omega, we go back to the, omega by definition is delta theta over T, right? That shouldn't be too hard. So what is your delta theta here? From here to here, what's your delta theta?
Pi over 2.
Right, so delta theta is pi over 2, and you did that in 16 seconds, so, you can answer that. And then it says, draw the omega vector. Oh, okay. Here's something we didn't talk about today, my own dumb fault. I forgot about this. We'll talk about it tomorrow. I hope. But it says draw the omega vector on your drawing on the left. So now you all think about this. I'll give you 15 seconds. And my hint is right-hand rule. Right-hand rule. Remember, you take your right hand and you curl it in the direction that you're going. And then if I'm curling it this way, my thumb's pointing up out of the page, that's a positive. If my thumb's pointing into the page like this, that's a negative. So if you you put your hand along the axis, along the radius, and you curl your fingers, okay, into the direction of motion. So which way is your thumb pointing? Oh,
Down.
sorry,
Negative.
yeah, I know. I forgot to turn on the comments. Okay, we only have one chat. Jacob asked, would it be negative omega? Yes. See, oh, that was the hamster question. On the hamster, wasn't the hamster going clockwise? Oh, no. Hold on. Back to Jacob's question. I may have screwed you up. How many minutes? No, that's the ant. Oh, die. All right, Jacob, give yourself a point there. Give yourself 2 points because that's a pretty big oops on my part. He's running clockwise, so you're right. The answer is going to end up being, I guess I'm not wrong, I just never answered it, but the answer will end up being negative because it's clockwise. So you should have a negative, still give yourself 2 points for pointing that out. Negative omega because it's clockwise. Okay. Now back to 16. Oh. Okay, so 16 here. So that's also, right? That's also clockwise. From looking down on the courtyard from above, that's clockwise. And so how would you show a clockwise, how would you show that? That makes it a negative. How do I show a negative vector then on a page? How do I show a vector going into the page? Oh, you can either chat it up or you can say it.
Would it be inverse S?
Well, inverse S is that's the units, but I want to know, how do I show the symbol? How do I show the vector?
Is it the circle with the X in it?
Yes, right. So I think Roman said that. So it's not the circle with the dot. That's the vector coming out of the page. And then you're correct, Roman. And so there's a zoom point. But for the second zoom point, Roman, tell me, where would it be? Where would you draw that X?
I'm sorry. I just had to let the dogs out, so I just kind of came back and heard the question. I'm sorry.
So anybody where would you put the vector? How would you show that? I agree, it's an X with a circle around it, but where would I put that on the drawing? Anybody know? Somebody's got, oh, here we go. Okay, so Jacob said it'd be at the origin. And yeah, I'll give you a point for that, but it's more, I guess it's not really the origin, because you might say that's where he started, that's the origin, but it's not really the origin here. It's the, I think I know what you're saying, but it's really the axis of rotation. So you always put omega at the axis of rotation. So axis of rotation. I'm glad we're working this problem because I know this was missed a lot last year by a lot of students. So you always put that, in this case it's an X. Now, if I made it an X on the take-home test, then what might it be on the regular test, on the in-class test, right? I mean, I don't put the same problem, and probably the way I think, and I haven't written the test yet, but I'm just letting you know, I'd probably make it go counterclockwise, right, on the in-class test. I may or may not, but that's how my mind works. All right, so C says determine your velocity. How do we do that? Looks like it's that old, once again, it's that old V is equal to R omega. Boy, you use that all the time. That is an important equation, obviously, because we use it all the time. All right, so you know R is 32 feet. You know omega, you got omega right here. We went pi over 2 in 16 seconds, so pi over 32, and just plug it in. All right, I'll let you finish that one. And I will, like I say, I'll post the key with answers. These are all kind of half worked out, but I'll post the key with answers Sunday night. So I know you're turning it in Thursday, but remember, just like take home test 1A, where I spot checked, but you got credit for a lot of participation. I did spot check some problems. I'll do the same thing here. Just don't leave things blank. Always make sure you show the good old college effort here on every problem. And you're going to get, even if you're wrong, you're still going to get some partial credit. But I do go looking for blanks. If I see those, that's automatic -6, -8, you know. Okay. We're getting a bunch of these. Oh, look. 4A, 4B is what we were just talking about. Clockwise, counterclockwise, you know, angular velocity, what we just got finished saying. Okay.
Can we do,
Go ahead.
can we do number 2, A and B really quick?
2A and B. What the? Why did I put? Good grief. Okay, let me find 2 then. Oh, okay. Use a label drawing to help you describe what a radian is. All right. So here's my, probably good to look at that again. So there's my delta theta. There's my delta S. No, okay, and there's my R. Now, some people would just say S, like arc length, but my thinking is this is S1, this is S2, which, fair enough, I get why you might not like that, but delta S is like S2 minus S1. So I'm trying to treat it like I would delta X. Okay, and this would be like theta 1, theta 2. All right. Anywho, so use a to help you define what so a radian is simply radians in general are delta theta equals delta S over R. So it's just a ratio, whereas that's equal to meters as far as units go, that's equal to meters over meters, which goes away. Or it could be feet over feet or miles over miles. But the point is that it's a distance over a distance, and so units cancel. And that's really cool because it makes radians very convenient to work with in physics because they don't have units. And that's nice. It kind of screws students up because they expect everything to have a unit, but it just doesn't have one because it's a ratio. So if I say 1 radian, I mean 1 radian is when looks like just happened to be that I made this, but it looks like it happens to be about 1 radian. But 1 radian is where this arc length is congruent. And that's a weird thing to say, I know, because it's a curved surface. But this arc length is congruent to that radius. And when that happens, that's 1 radian, which happens to be about 57 degrees. Okay. I don't care that you know that, but that's what a radian is. Okay. We're down to 20 minutes. Now, we've looked at a lot of these. 3, 2, 4, 5. 5 we got pretty good look at. 6 we've done. 7 was kind of a hard one. But I think, did I give you enough on 7 that you're supposed to find omega? I didn't.
You did.
You get a really small number though.
Yeah, I got a really small number.
You would. Yeah, because radians per hour wouldn't be 4.2 means it goes 4 in an hour, it goes 4.2 in radians, which is pretty big. But then you divide that by 3,600. So even though it's moving at 70,500 miles an hour, it's got a really small omega. 8, we haven't looked at 8 yet. 8 is a bunch of those. Maybe we ought to, because I think you can do 8 and 9. That's just converting. People are still messing that up a little bit, but you have a couple of worksheets and a couple of help videos. But 10, 11, 12, let's try. You want to try one of those?
Can we do 11?
All right, let's look at 11. So 11 says, what's a better way to write? Okay, so in other words, my number's huge and my unit's small. And so I want to find some way. So I just kind of, not in my head really, but milliliters, and then I got 10 to the 9th. So I'm going to jump up 9 slots. So milli is 10 to the -3. When I jump 9 slots up, that puts me at 10 to the 6th, right? Because -3 plus 9 is 6. Well, that puts me right at megaliters. So the answer there would simply be 8.00 megaliters is a much better way of saying it. So we're using something little milliliter scale, which is where you know, for teeny amounts of water, and we're trying to describe this huge big bowl of water. So megaliters is a better example. I mean, a liter, you think actually we're doing that's a swimming pool. A liter of Coke bottle, you know, liter, and now you got 8 million of them. So yeah, that's probably a swimming pool.
Can we do number 10?
Right, I was just looking at 10. 10, now we have a huge number again, still the same number, but now we're saying microliters. So what's a better way? So I go, okay, microliter puts me at 10 to the -6th, and I'm going to jump once again 9 slots up. That puts me at 10 to the 3rd. So that'd be kilo. So that's all you say. That'd be 8.00 kiloliters. Okay. Something like 3, about close to 4 liters in a gallon, somewhere in there. So
Mr. Askey?
yeah.
What if it doesn't land on like
Okay, well, let's do one that doesn't land. How about 12? Because I thought, well, that's pretty convenient. So 12, we have, all right. So now we're looking grams, and grams is 10 to the 0. Now I'm going to jump 10 above that. So that puts me at 10 to the 10th, but that's going to land between 10 to the 9th and 10 to the 12th, right? So 10 to the 9th would be gigagrams, and I am 10 bigger than that. I'm 10 times. So it's not 5 gigagrams, it's 5 times 10, or that would be 50 gigagrams. That's really sloppy. I'll clean it up when we're. I'm leaving 13 for you guys. I'm not working 13. You guys can talk about 13 on Facebook. You're getting a little bit more Facebook chatter, but we need more. I need to see a lot of Facebook chatter back and forth, because as the year goes on, I don't know what I'm gonna do. I can't say that. Who knows what I'll do? We did 14, did 15, did 16. So we've kind of looked at all of them. Any other questions? Still got 15 minutes, but I'm certainly willing to cut it off short.
Did I miss 4A and 4B?
4A and 4B, we talked about it when we were doing the other ones, but just remember, counterclockwise that's right-hand rule. So this is all right-hand rule stuff. So counterclockwise, going this way, we said that then my fingers are in the direction of motion. My thumb comes out of the page. And so you indicate that omega, that would be considered positive omega. And positive omega is a vector coming out at the axis of rotation. So in that case, you'd put a circle with a dot. That shows your thumb coming out of the page. And then, yeah, clockwise, now we're going around like this. And now this axis of rotation is right here. And this time it's an X. Because that means that my right hand doing this. So my right hand's curling around my thumb. And this is not trivial stuff because in E&M, in electromagnetics, everything's about right hand rule because things are always, you know, like electric field, like when I have an electromagnetic field, electricity goes this way and magnetism goes this way, always perpendicular. So there's always what's called a curl. That's why motors, you know, rotate because putting those magnetic fields cause, you put magnets in there, cause the thing to rotate. That's why all motors, you know, because of this, because of what we're doing right here. Everything in this class has huge applications to quantum, sometimes not, but to relativity, to electricity, magnetism, to all this stuff you're going to do the rest of your life if you stay in physics. You'll learn it all here as a foundation. So there's nothing I talk about that's trivial. It all is application. All right. Just trust me on that. Who cares about the right-hand rule? Well, you'll be the jackass doing this in college, okay? Because you got to. That's how you have to understand it. All right, so Ryland has surfaced. He may have a question. He surfaces, then he asks a question like a German sub, and then he goes back under the water. All right, so Ryland came up to ask a question. Maybe he's signing off.
I was actually just kind of wondering on the gold standard.
Yeah.
Oh, wait, never mind. We worked that part.
Well, we worked it, but I mean, I'm willing to answer any questions. I think we're pretty much done with it. There was a couple of more conversions we had to do. We're trying to end up in milliseconds, and we might as well play with that. So let's get my green kill pin out. We have time. So 50 to feet. Oh, I just did these two because they were given and said, hey, if they're given, you know, you got to put them in there. So the feet die, inches gets killed. Now I got meters and nanometers. So obviously the next move, right, is to do nanometers to meters. So we have 10 to the 9th. Don't do it the wrong way. Nanometers in a meter. Don't say 10 to the 9th meters in a nanometer. That's very common. It'll make your answer off by 10 to the 18th. You won't lose that much, actually. Oh, I wasn't supposed to do that. My bad. Green is used for killing you, sorry. Nanometers, meters. So now my green kill pin comes out. Nanometers, nanometers. What I got left to do? Oh, I got 2 with 1. I'm turning up in milliseconds and I got microseconds, right? So we go microseconds to milliseconds. So that bothers some students. Like students want to go from microseconds to seconds and then seconds to milliseconds. Don't do that. Just go microseconds to milliseconds. So microseconds down here, it's got to die. And then milliseconds up top, I want to keep it. Well, how many microseconds is 10 to the negative 9th? Milliseconds is 10 to the negative 3rd. So the difference is 3, right? So there's 10 to the 3rd microseconds in a millisecond. And now I bring up my green kill pin, kill the micros, save the milli, circle what you're going to save. And then you put your triumphant double slash. And at this point on the test, at this point, I would move on. I wouldn't solve it because this is worth 8 points. You're going to get at least 7 out of 8. It's going to be worth a lot more than 8 points. It's probably worth like 30 points in the test. And you would get like a 28 out of 30 if you stopped right there. You know, just rather than lose 15 points on a dumb problem you could have done easily, you run out of time. I hate, you know, I was thinking this, this long drive down to Austin, you know how much I hate time tests. I hate pressure. I don't deal well with time constraints. I never have really. And I would like to just say, you have all the time you want to take this test. But the thing is, that's not the way they do it in college. I mean, they time you there too. So you have to develop these triage techniques. If I gave you 3 hours to take the test, you would never learn kind of how to triage things, you know? I don't like to think fast. I don't either, but that's what I'm saying. This is a triage technique. Stop, move on, come back at the end, because the AP test is also timed. Come back at the end when you have the luxury of time, and then work it. That helps in the ACT as well. Yeah, well, go ahead. You have to answer ACT, but we don't give you partial credit. Okay, so I'm glad we worked that one. And you guys gave me the answer. I think you're getting 29 or something. What were you guys getting on this on Facebook?
29.85.
All right. So that's what you would get, right? I mean, take a quick glance at this, and that looks. Oh, here's a shortcut. Check this out. What I would do is, yeah, okay. Let's say we have time. We go back and do it again. All right. So I have 68. I just write the numbers out. 68 times 0.3. I forget the unit. I don't need the units anymore. Times 10 to the 9th. And then that's my 3 numbers on top, divided by 57. I do this in my head, that, or just in the calculator, times 12. Like I don't need to see this black step I'm doing. I don't need to see this. I mean, if you want, that's great. 10 to the 3rd. And so if you line up your times 10 to these, you can just quickly, mark it out and put 10 to the 6th. It's a little faster. So you got 68 times 0.305 times a million divided by 57,900, whatever that is. Okay. So that's also a way to know if your answer's in the ballpark. You can kind of just do by tens. Because look at this. Oh, one more last thing. That 68 is 10 to the 1st, something 10 to the 1st. The 0.305 is like 10 to the negative 1st. Then we have 10 to the 6th after we did little quick, converting. And then 57,900 is 10 to the 5th. Yeah, so that's like 10 to the 5th down here. And then 12 is like 10 to the 1st. So I'm just looking at powers. I'm guesstimating. So those cancel. I got 10 to the 6th over 10 to the 6th. Puts me in that 20s, 30s, or 10s, that range, which if it's a nerve impulse coming from my toe to my head, sounds about right. In other words, it's not a billion seconds. It's not a billion milliseconds, which would be way too slow. It's not 0.00001 millisecond, which is way too fast. So it's in the right range. So if I didn't have time, didn't have a calculator, I would call it, okay, I'd say that's probably good. I would say I didn't screw up. Like I didn't do this. That would tell me that I didn't do this. I didn't say 10 to the 9th under 1. You see what I'm saying? It's a quick check. Yeah, once again, triage stuff. It helped me a lot. Once I started triage techniques, taking tests in physics, because I have anxiety, it helped me with my anxiety on a test, because I would my brain would freeze. Because I'd feel like, oh man, I'm on problem 3 and everybody else is on like problem 10. And I'm sitting here, I can't, so I'm spinning my wheels. So I would just kind of do as much as I could and then move on and come back. That helps a lot. I used to be a perfectionist. I'm a reformed perfectionist. Okay, physics will do that to you. It'll cure your perfectionism or else you'll go crazy. All right, I think we've covered everything. Now I'm just, I'm down to 18 participants and 7 of those are asleep. Question, Liam.
So we can log out now.
Oh, you can log anytime you want. This is come and go.
Thank you so much.
You bet, not required. I will not be offended if everybody logs out at once. All right, so I've got this recorded. I'm going to go ahead and put this on my YouTube channel. It should be ready to go in about 30, 45 minutes, okay? Are we good? Any last thoughts? Let me turn this on. So virtual kids, let me stop sharing. This is the only time that I'll get to do a live session with you guys. So anything, any kind of housekeeping that you have a question about? Now you can go check the wrap-up video, but anything that didn't make sense on the logistics of what's happening, always check the key, always check the calendar and stuff. I gotta update that. I see, I just realized. Okay, so for virtual, come by my port, either get a stack off the porch or oh, I only got a few of you left, but so what is your thoughts on like coming into my room like from 1:30 to 2:30 or something? You pick a time on Tuesday afternoon where you can park in the science lot, come into the science building and leave and not really go in the building, not go to the rest of the campus at all, as far as test goes. Would that
I was just zooming it.
okay? So Zoom, right? I mean, I'm willing to Zoom. It seems kind of weird to me.
I could do like the outside thing, like where we
Oh,
sit.
right, the
Lawn.
the west lawn. So so you know we need like, because there's some things that just virtual kids really care about, and maybe we need I don't know, we don't want our own Facebook group, but maybe we need some place where just we can talk. Anyway, I don't
Doesn't
know.
Facebook have that kind of meet thing?
It has like a room, and maybe that's a good point. Maybe we could think about that. Okay, so anyway, I'll talk to you guys, and we'll think about that room thing at Facebook. That might be a good idea. All right, so I'll see you guys later on, and see you on Facebook anytime. All right, bye-bye.